now that we know how to represent data inside a computer, how to represent programs inside a computer, and also the process of taking a program that is in a human readable format and converting it into a set of encoded numbers that a computer can represent, it's a good time to sort of take a step back and say, okay, how does a system, right, how does the computer actually sort of do all of this, right? And there is a key piece of software that plays an important role in doing all of this, and that is called the operating system, right? So let's look at the, quickly review what we mean by programming in the first place, right? What do we understand by the process of programming? One of the first things we need to do is to actually write the program, right? So typically a computer can be thought of as, there's a monitor, there's a box out there which actually has the CPU, memory, disk, etc. inside it. There is a keyboard, mouse. This keyboard and mouse are clearly sort of input devices. They are ways by which we interact, right? We provide our inputs to the computer. The display is an output device, right? We get to see what the computer has understood of whatever we are trying to do. In certain cases, this display could also double as an input device if it's a touch screen, for example, right? At the same time, the box out here, right, essentially takes care of actually storing the data. So files, storage, all the encodings, the CPU itself, the memory, all of that is inside that box, right? If you really finally look at it, this whole big box that you see over here, the actual CPU, the relevant part of it, is going to be one tiny dot sitting in the middle, right? But that's okay, right? We already know that there is a lot more to the computer than just the processor itself, and the net result is when we interact with a computer, we don't even get to see that chip. We don't really sort of even think about the fact that all these instructions are flying back and forth and are being interpreted in different ways. What we see is a desktop, right, which typically nowadays we have got used to this. It's a metaphor, so to say, right, where we try to think of a computer desktop as similar to an actual desktop or a tabletop on which we would work, right? What would you do on a tabletop? You would have your books or papers or files open. You would use input devices like a pen or a pencil to actually annotate them, mark on them, and you would move files around from one place to another. So once you have finished processing a piece of paper, maybe you are reading a letter or writing a letter, you sign it, put it to a side, ready to be mailed out, right? Let's say that you are reading something that was sent to you by someone else. You read it, process it, you might make some markings or annotations on it, and then you put it aside. A similar kind of metaphor is what has been used in the context of computers. So the computer desktop also says that you can have this image of files, each file containing something that is relevant in some way or the other, some text or maybe a picture or a movie, music, right, or a program, right, as a text file. So the typical kind of programs that we normally interact with in the computer would be a file manager, Windows Explorer, the Finder in a Mac system, right, Nautilus in a Linux GNOME environment, and so on, right. Probably the most commonly used one these days would be the browser, right, the web browser, Chrome, Edge, Safari, right, many Firefox, many different variants. Each of those is actually a program by itself, right. And similar to this, there are many different apps, applications, right. App is probably more common in the context of the mobile world or tablets or things like that, but the bottom line is there is actually no fundamental difference between the two, right. Either way, it is a program, a piece of code that is executing on the processor. The distinction between an app versus an application versus a program is more in terms of what was it that the person had in mind when they were originally writing it. From the point of view of the computer designer, these don't make too much of a difference. For us as programmers, one of the most important programs that you in turn are going to use is going to be what's called the code editor, right, which is, you can use any number of different kinds of editors. The one that sort of comes built in with Windows systems is usually called this thing called Notepad. which to be frank is not a good editor, right? I mean, it has too many problems and is not really the ideal kind of thing that you should use to edit code at all, right? But there are many different kinds of editors that can easily be downloaded and installed, which specialize in making your life easier when you are actually writing code. So bottom line is, you need to have this ability to run all of these different programs, right? File managers, browsers, code editors and so on, right? These are already multiple different programs that need to be running on your system that you can then use in order to do other things. Now, once you have written a program, the next step we saw was how do I compile the program, right? So the compilation process is a transformation, right? You basically take your input text corresponding to the program and convert it into the machine code, a set of bits that could be loaded into the memory of a computer and would execute as another program. So the compilation itself is another program, right? So now we have sort of run into this slightly tricky scenario. I am editing a file, which means that I am using a code editor somewhere. At the same time, I also want to be able to compile the program, right? Now, how do I do that? I can't be both editing and compiling at the same time, because after all, there's only one processor, right? So you might think, hey, but my system has like a dual core or something like that. You don't need a dual core to handle this, right? What usually happens is that the processor is fast enough that it spends a few milliseconds interacting with you to do the code editing, a few milliseconds as part of the compiler, and a few milliseconds doing something else entirely, right? And this millisecond time scales are so fast that humans can't really make much sense of them. It looks as though everything is happening at the same time, right? So even with a single core processor, it's entirely possible to give this illusion of multiprocessing, right? Multiple things happening at the same time, right? What that means is that there is this compiler that's going to be running, which is actually taking your input program and doing something with it. You could have an editor which could be a browser based, web based system, right? And we will be using something called Replit as a common way of entering and compiling code as we move forward, right? And along with that, somebody somewhere has to also be managing all the memory, right? Because your system has a certain amount of memory. You have some programs already running in it. There's a browser, there's a code editor. Now you want to run a compiler, right? Who gets which part of memory? Is any program allowed to access the memory corresponding to any other program? What kind of protection is provided between programs, right? And how do I sort of jump between the different programs fast enough that you can be fooled into thinking they're all happening at the same time, right? So there has to be something that is sitting behind the scenes and managing all this for you. Along with managing the memory, you also need to actually execute the program, right? Once you have finished the compilation process, once you have finished writing your program, you need to execute it, which means that somebody or something has to take care of loading that program into memory, right? Remember the picture where the memory was divided into different segments and the output of the compiler could be either treated as the data output of the compiler or the code corresponding to another new program, right? But the point is, there has to be some entity or some piece of software out there that decides where in the memory of my, where in the physical memory of my system does this program actually go, and when do I actually start running it, okay? So altering the flow of control, deciding when to jump to a new program and then what to do when that program finishes, or what happens if the program needs something which it doesn't have access to, right? All of those things are handled by something called the operating system, right? And as I have put it over here, the operating system basically functions as a coordinator. It is also a piece of software. It is a program, just like any other program that you write, right? The operating system is also a program. It sits somewhere in the memory of the computer. It has a bunch of machine coded instructions which are executed one by one. They are fetched based on the program counter from memory and executed one by one, right? So in every sense, the operating system is a program. The only difference between this and other programs is that this has the ability to sort of coordinate among all the other processes and programs that are running inside the computer. It is what gives you the illusion that multiple things are happening at the same time. Okay. So it is, like I said, it's yet another program. The important thing is it is the very first program that is executed on startup, that is as soon as the computer is switched on, so to say, right. It coordinates the loading and executing of the other programs, and one word that is typically used in this context is that it is what's called a kernel, right. And the reason why it's called a kernel is because unlike most programs which usually try and read from a file, display something on screen and so on, the operating system kernel, yes, is capable of doing all of that, but fundamentally its job is more to just make sure that those facilities, the screen, the keyboard, the network, the files are available to other programs, right. So you very rarely interact directly with the operating system. You always interact through some indirect means by calling some functions as part of some other programs which finally make the operating system do something for you. Okay. So sort of to summarize all of this and put it all together, there is one term that is worth understanding in a little bit more detail. Some of you may already know about this, others, almost all of you have probably heard the term, right, and the term is booting, right. We talk about booting the system or rebooting it, right, and what exactly do we mean by that, right. Now where this comes from, right, is the fact that there is actually some kind of a chicken and egg problem in terms of how a computer goes about doing things, right. Because like I said, if I want to execute a program, I need some way by which the program first gets loaded into memory, okay, and once I have done that, yes, I can execute the program, and then I can, once I am done with it, I basically get out of it, right, I am done. How did that program get into memory in the first place, right? And that's not a trivial problem to solve in general, right? Because one way of doing it is that I have some specific memory that is created as part of the entire computer system, which literally says, okay, these are the instructions that are there, and that's it. Every time I switch on the system, the computer will just execute these instructions and nothing else. Okay, there are systems like that, right, and in fact typically those would be what are called embedded systems, right. Nowadays of course embedded systems means a lot more, but in previous generations at least, right, an embedded system could literally have that kind of functionality. It has a very specific set of instructions that are executed each time it is switched on, okay, and the only way of doing that is you literally program the program that you want the system to execute, you put that into some kind of a read-only memory and put it in such a way that as soon as the system switches on, it will start getting those instructions one by one. But that's not what we expect of modern computers, right? We want them to have different features, we want them to have like a nice graphical interface, we want them to be able to operate with the latest and greatest graphics cards that we have got. If I plug in a USB drive, then something has to be able to recognize what's on the drive and then play the music from it if needed, right. There is a whole lot of work that a modern computer is expected to do, and if I try to put all of that into a fixed read-only memory and put it into a chip, right, it's first of all inflexible, and secondly it also just will make the chip just too big and unviable to produce in practice. So instead the procedure that is used is a slightly circular procedure. What we say is, as soon as the system is powered on, that you switch on the computer, the program counter, right, which determines which is the next instruction that I am going to load, is initialized to some known value. How is it initialized? This is literally in the hardware, right? The circuits are built in such a way that as soon as I switch it on, I guarantee that PC will have a particular value. Is that value 0? Is it something else? That depends on who designed the system. Okay, there's no guarantee it has to be 0. It could be, in fact in most cases it's not 0, it's usually something else. Now doesn't matter like where it is, the point is PC points to some known value out here. So now if I could sort of figure out some way by which I make sure that the instruction out here is something known to me, then I have a starting point. And that's usually what we do, right? We take one small chunk of memory and map it, right? After all, what do I mean by map it? Remember how memory is organized? Whenever I give an address, I am going to get back something from that address, whether that is actually data that is stored over there or it's data that's coming from a peripheral or from a read-only memory, we don't know. The computer doesn't know and doesn't care. Which means that we could then create it in such a way that this particular region of memory is preloaded with some code which has a very minimal functionality. Okay, what is that minimal functionality? I want it to be able to display some kind of a picture on the screen, picture or text or something on the screen to interact with the human being, and also to get some kind of maybe allow the human being to press something on the keyboard to possibly make some changes in how it works. And most importantly, it should also be able to do some kind of reading information from disks in a fairly standardized format, right? It can't be a very generic program, because if I need to be able to read any arbitrary kind of disk or make use the graphics features of any arbitrary graphics card, those are in general going to make that program too big and bulky, right, and not really convenient to use. So naturally I expect that this is going to be a fairly small program, something that doesn't change often. This is called the BIOS, right? It is a BIOS basically stands for the basic input output system, right? And it might be that you have come across the term BIOS at some point while booting your computer, right? At the very least it might have flashed some message saying this BIOS version whatever it is before it starts showing you the rest of the computer screen. Now the BIOS is a form of read-only memory. What I mean by that is it's not expected to change. The computer manufacturer puts it in there and that's it. That is not the operating system. It is only the basic IO system. It just allows you to start reading from somewhere else. Now what do you do with that? The BIOS starts accessing external storage. And by this storage, what I typically mean is the hard disk that would be attached to your computer. Okay. The BIOS knows how to access it. It doesn't know how to sort of do it in an optimal or fast manner or anything like that, right? But it knows how to read data from there. And that's all its job is. It doesn't have to be efficient, it doesn't have to be fast, it just has to be able to get data out of the storage, load that into another part of memory, and this part I am going to say corresponds to where my OS is going to be, right? Now you see where we are going with this, right? Because the storage just has a chunk of bytes on it, right? And what I am going to say is the BIOS job is just to take those bytes, put them into a new area in memory, and then jump to that part of the memory. Okay. Now this memory is essentially what we call a random access memory, RAM. Okay. People sort of think of ROM and RAM as being opposites. They are not, right? So you can have a ROM that is also a random access memory, right? You could have a RAM that is also read-only, right? So what the probably the more accurate word for this would be a read-write memory or something like that if you wanted it to be the opposite of ROM. But what is more relevant for us is that it's random access. It is something that can be quickly and readily accessed by the CPU at any given point in time. And more than anything else, it's just become a habit to call it RAM, right? We don't even say how much memory does the computer have, we say how much RAM does it have, okay? But this is what RAM refers to. What we do is we take part of the data from storage, put it into a part of the RAM, and now the PC has been altered, right? It now points to some part inside this OS kernel. So now the instructions that are executing will now correspond to things that are sitting here in this part of the memory, right? Now I can start doing more fancy things. Why? Because this OS kernel that I have can be much larger than the BIOS. The BIOS necessarily has to be small, right? So that it can be put in ROM and does not get outdated with time. It's not something I want to update or upgrade at any point. It's just something that should have basic functionality. but the OS kernel can start doing fancy things. It can basically have like more advanced drivers for my storage, which means that it can start reading data fast from the storage and start loading more complicated applications, including the graphical interfaces that we are all used to. Okay, those I am going to call apps or applications or programs, right. Once the OS takes over, it basically loads the apps into memory as needed, and from there we basically have the entire system ready to run. Okay, and the analogy that is used for this is effectively that in some sense what has happened is the computer is trying to fly by pulling itself up on its own bootstraps, right. Imagine that you wanted to go up into the air, right. So rather than getting into an aeroplane or something of that sort, you just hold on to your shoelaces and pull, and just by doing that you are somehow able to go up into the air, right. There is nothing, it is in other words a restatement of the chicken and egg problem, right. Which came first, the chicken or the egg? We do not know. In this particular case, we have a specific solution, we have one particular route by which we are able to get the entire system working, right. So this term pulling yourself up by your bootstraps in turn comes from a fairy tale kind of a story, where a person was supposed to have essentially pulled himself out of a swamp by basically pulling on his own hair, right. Now the analogy again is not, it's not a very great story at this point. All that matters is that the term booting or bootstrapping comes about from this. What is important to recognize in this context is how the entire system works. There is an interplay of the hardware which takes care of making sure that the CPU comes up from switching on, right, in a known state with the program counter pointing at a specific place in memory. The computer manufacturer has to make sure that in that place in memory there are some instructions that will handle the basic I/O and thereby allow us to access a disk perhaps, right. That in turn we need to make sure that on that disk there is a lot more useful information which basically allows us to activate the different peripherals, the keyboard, mouse, video, network, all of those, and load data into the memory of the system, which in turn will then start loading programs and executing them one by one. Okay, that is the process of booting a system, whether it be a phone, a laptop, a mainframe server, right, a data center machine, or an Arduino, right, a tiny little microcontroller with a small amount of memory associated with it. All of them follow substantially the same process in terms of how they get activated. Okay. And once again, the reason why as a programmer you would probably want to know about this is probably much more relevant for those interested in embedded systems, but the process of knowing how this works, it can be useful for anybody who is using a computer, right, because at the end of the day when you get into this thing where there is a conflict or a problem with the different parts of the computer, you need to know where to look, and this is an important part of the process of debugging.